Okay, so yesterday we were talking about how to compute, like how to get deterministic algorithm to compute min cut in the graph, right? And just to recap, the idea is, like intuitively, the idea is super simple. Because first of all, if you start with an expanded decomposition of a graph, and you know that each part is kind of expanding inside, then very intuitively, if you have any min cut, it doesn't let me, sorry. Intuitively, if you have any min cut, what you expect is that, let's say the expanded decomposition is like this. What you expect is that, roughly speaking, the min cut should kind of respect this partition. It shouldn't just cross some expanded like this. Just because in expanded, there should be a lot of edges crossing it, right? So what you expect is okay, it might kind of, min cut might look like this. It might cross a bit of expander, and that's fine because for expander, if this thing is small, it doesn't really guarantee much about the thing that the number of edges going out. Yeah, makes sense, right? Yeah, and so what we did in class is that we expect that any min cut shouldn't cross the expanded too much. So what we do is to kind of find some region inside expanded that we kind of know that is safely disjoint from expander for sure. Disjoint from min cut for sure. It doesn't overlap with the min cut. So we identify this thing, and this is what the step of shape and trim did it for you. We identify this part. Okay, so that is we did a lot of calculation in class, but here is an intuition behind it, really. Okay, and in class, I show you that the total number of, we know that the way we, when we try to find expanded decomposition, we find it with a notion of expansion. So what we did is that we return V1, or in class we use x1 up to xk, such that for each I, the expansion, the psi of each of the xi is at least 100. And the number of edges crossing edges is then something like what? It's going to be something like 100 times n times some subpolynomial factor, right? So the number of edges crossing expander is not too much, and then we prove that even the part that we kind of trim out further here, it's just a constant factor away from the number of intercluster edges. So we proved that the total number of edges that remains after we contract. After we contract the thing inside, the number of edges in the contracted graph is just still like something like this thing, which is m over delta times this thing. Okay, so that we bound the number of edges, like the graph shrink in the number of edges. So this is we show in class. Okay, now I want to ask you, like now we want to bound the number of vertices. Like we want to show that the number of vertices is n over delta, roughly. So first question to you, to think a bit, is that in this expanded decomposition, how large can this K be? When you know that the mean cut is, if mean cut size is lambda, how large can K be? I let you think for like maybe a few minutes. Say it again. Not quite yet. Like for example, if the graph is just a path, then there can be really a lot of the cluster in the expanded decomposition, although lambda is super small, right? Yeah. So the intuition should be that, okay, when lambda is large, then that should mean cut is large. It means that the graph is more connected. So, yes, now like so actually n over lambda is correct. And let's just, but the intuition that I was going to say is here, right? Like the larger lambda is, the graph is more connected. So it should be like a bunch of things that looks like an expander, the bunch of large cluster that looks like an expander, and that should mean that like yeah, right, yes.
Basically, the idea is that there are too many clusters, you can just pick out one whole cluster.
Yeah, right. So let's just try to see this. So first of all, if you look at, so let me just draw again here. Here. If you take any xi, any expander here, and just look at the cut here, right? This cut is just some cut in the graph. So the number of edges crossing this must be at least lambda. Yeah. And this is true for every of the xi. Like for each of the expander cluster, you consume at least lambda edges along this intercluster edges. But how many intercluster edges are there? Something like n. So that's why like the number of clusters can be at most n over lambda. Yeah. So k is at most n over lambda.
Is it like phi and not expanded? It should be as like 100. Yeah, 100, but 100 is vertex expansion, so it should be edge expansion parameter into an over lambda.
Edge expansion parameter. I don't understand that, sorry.
So there can be at most phi and intercluster edges, right? So it should be phi and over lambda.
Yeah. So here is really like, so it's really just crossing edges here by lambda, and this now depends on how you choose the parameter in the expanded decomposition. Yeah. So in this case, it's just something like this much over lambda. Okay, thanks. Okay, so now we know that, okay, not too many edges are like, not too many components are there, actually. Yeah. And now, so next thing is that, so now we want to know like how many nodes, like when you trim and shave, how many nodes you can trim and shave. So so far, like if we contract everything in the expander, like if you just perform expanded decomposition and you contract, then there is like then there are just at most this node, right? Yeah, but we want to know more because we might trim and shave, and the node that we trim and shave will remain in the contracted graph. So now we want to say that these guys, they are just like in total overall expander cluster. In total, the number of trim and shave node is at most these two. So why is that? Well, this is just because like this is gonna be something like similar to here. Like basically, okay, let's just look at this. Here we will just use the fact that the number of edges here is something like n. So number of edges in G prime is something like n. But for each node that you trim, you contribute at least something like lambda edges into the G prime. So for each of the time that you trim, you contribute actually delta O of delta edges into G prime. So that's why there can be like n over delta edges, n over delta trim nodes. Sorry. Right. So just to draw things. So let's say this is your expander part, right? And then let's say this is a node, and you trim this guy, then one sec. Am I correct? Sorry, one sec. Let me think, maybe.
Similar to edges, because edges are in constant fraction and so number of new edges over
Let me see. Okay. Yeah, I think it's, so let's try to do it together. Yeah. So forget what I said just a moment ago. Yeah, sorry about that. But it's like this. Look at this graph G, and let's say that, okay, this is expanded decomposition, and then in graph G prime, there will be like this node that you call like let's call this part that you contract a supernode. Okay, and you know that the number of nodes that you contract is at most, like this number of supernode is at most the number of expanded cluster. So it's at most k, which is n over lambda. So that's fine. You bound the number of supernode. Okay. Now let's just try to look at the regular nodes that also is in G prime, right? Each of these will have degree at least what in G prime? Well, degree will be at least delta. No, like this guy will have like each regular node has degree, like regular node U has degree in G prime equals degree in G, right? Which is at least delta. And now it just follows that the number of regular nodes must be small, just because the total volume, the total number of edges in G prime is something like n. And each of these has large mean degree. Like each of these has large degree. So yeah, that would do it. Yeah. So actually I don't even need much thing to like. I don't even need to bound this like in a different way, right? I know that like yeah. So like this supernode become one node, and it must have the number of edges going out of it at least lambda. This guy is a cut as well, so the number of edges going out of it is at least lambda. So the number of nodes is at most n over lambda. Yeah, I even like I don't really need to say this first, I guess. Yeah, right. We don't need that to like. If we just look at yeah, we really just like use the same kind of argument here, but instead of saying that this is the number of crossing edges in the expander decomposition, we just say that yeah, the number of so the direct argument should be just the number of nodes in G prime is at most the number of edges in G prime over lambda. And just because each of the nodes correspond to a cut in original graph, and that cut has size at least lambda. Make sense? Yeah. So you have this. Okay.
So the other one will be better bound.
Yeah. So the other one here you have delta, which might better. Yeah. But the number of supernode here, I only get lambda here. So yeah, so far I only get this bound. There must be a way to actually get this bound. Do you see how to do that?
For all regular nodes?
For regular node, we are done.
We get that, and for the supernode we get that, so we can add that.
But for the supernode, we don't have n over delta yet, right?
Yeah, n over lambda.
Yeah, so is there a way to actually prove that we really get n over delta instead of n over lambda? Like, I know that this is true, so, but how to prove this? Let's see. Do you guys see how to do this? I don't see it. Maybe it's simple.
So can we use the properties of trim and shave to see each and every expander after trimming and shaving is not just lambda but much more than lambda? Like, of course, that is the naive bound, right? Any cut is a mid cut. Any cut has no mid cut is a naive bound. But we have some more structure in shape.
I see. Like, you are saying that if you know that this thing remain because even after trim and shave, the number of edges here shouldn't be just lambda, but should be at least delta. Yeah, so let's see. No, I don't see this because in principle, you might actually have like just like this is a click and this is just one edge outgoing. Like let's say that the graph, you have the graph like this. Like there is just this edge and this thing is a click. Then this thing you wouldn't trim it, right? And like this thing will be cut, but you wouldn't trim anything further. So the number of edges going out of this is one. So
Then that says it is tight, right? Then that says lambda is tight.
Lambda is tight.
Like,
oh, tiny. I see.
No, tight, tiny. Like if this is the example, then always.
Yeah, but I mean, this thing can be lambda exactly, but delta might be bigger than lambda.
So I'm saying this is an example where you actually get at most lambda lambda plus super. Then like how then the
Yeah, I see. Is it? Okay. But I thought this bound is true. Anyway, maybe one of you can try to check offline. I try to check if I think this bound is true. Yeah. But I don't know. Maybe I misremember it. But anyway, what do we have here? We have that the bigger the lambda is, the more edge, the larger edge connectivity is, then you can shrink the graph more, and you really preserve exactly non-trivial mean cut in the graph. So that's quite neat. Yeah. Like most of the algorithm that is about compressing graph, you kind of sacrifice some approximation, but here this is exact. Yeah. Okay. So I will talk about this maybe in the video. Okay. And just want to mention one thing about cut specifier algorithm. Can anyone remind me how did we compute cut specifier of a graph?
By reweighting the edges with the log square and lambda.
Yes. Yeah. So that is the algorithm that just work. Like if you take any edge E and just sample it with probability this much. Like for each HE, you take this sample with PE, which is something like 1/0 lambda E, where lambda is the connectivity between the two endpoints. Then it just works. Okay, but I didn't prove it in class why it works. I will still not prove it. But just to compute lambda E might be hard to do in general graph, right? It's a MaxFlow problem. And so we did something to make it very fast. So how did we do that? Like what is the approach? How did we avoid computing lambda E? Say again.
You use something like that, lambda prime E to approximate, right?
Yeah. So what we say is that actually, if the graph is an expander, then you can approximate lambda E very, very fast, right? So in expander, and this is like in homework 1, actually. Yeah, so if a graph is an expander, then lambda E is something like, and E is this. Lambda E is going to be something, what? Degree of U, minimum of degree of U in V. And this is like within 5 factor. So this is why like lambda E can be approximated so easily if the graph is an expander. Just compute the minimum degree between the two ends. But how can we assume that the graph is an expander? Yeah. So we do this repeated expanded decomposition. Like you get expanded decomposition first. There are some still remaining edges. Just take that graph and perform expanded decomposition again. And then you will get like really just a union of expander. Right? Once you get the union of expander, you now can specify each of the expander using this trick. It's now very fast on each expander. And what you do next? Just combine everything. Just union all the specified thing together. You will get a specifier of the whole graph. Right? So this is it turns out to be a very powerful trick, actually. So, like, for any problem that is composable, what you do, like, if once you know that the problem is kind of composable, like spanner or cut specifier, they are composable, you immediately just can assume that the graph is just an expander and come up with fast algorithm on expander. Right? An expander just have a lot of property that you can exploit, and you come up with the fast algorithm on that, and you're done. For here, the fast algorithm is simple like this. Okay. So in class, actually, Chaitanya mentioned one thing about spectral spatifier. I want to tell you what are they, and want to tell you also that the same algorithm here just extend to that. Although spectral spatifier is is strictly stronger than cut spacifier. So what is spectral spacifier? Okay. So spectral spacifier, maybe I can, let me, so it's just very similar. If instead of cut, this is spectral spacifier, then spectral equivalent. That's it. But do you remember what is this thing? Like we have defined in class once. Do you recall this?
Just indicate a set of subsets. It is for every x belongs to quadratic forms.
Yeah, so just to recall, here we said that H is spectral less than G if L, the Laplacian of H, is less than Laplacian of G for all x in R to the n. And the reason why this is strictly stronger than, why this is stronger, at least as strong as cut spacifier, is that if you look at x when x is 0, 1 vector, then this is the same thing as saying, do you recall this? If x is just this, then what is this thing? Yeah, cut size, right? So, if x is just indicator function of a set S, then this is just a cut size in G of S. But you have this instead. Here is stronger. So now, one can talk about spectral spacifier. Given a graph, can you compute spectral spacifier? And so it turns out to be a useful concept because so I can only mention words here. So when you want to compute, this is just a buzzword so that you can link it to whenever you hear it next, in other in future. So when you want to compute Laplacian solver, or in the fast interior point method, many times in when you want to use a continuous method for graph problem, some linear algebraic method for graph problem, the link from between this method and graph is usually from via Laplacian of the graph, because Laplacian of the graph is like some matrix that is really associated with the graph. And instead of working with this Laplacian of the original graph, if you can get like easier Laplacian to work with, which is Laplacian of the spacifier, then it's good for you. Like it's just, you can just work with a Laplacian of spectral spacifier and like, so note that if the number of edges in H is small, then the number of non-zero in Laplacian of H is small too, right? So if your graph is sparse, then your matrix is also sparse, and that's why it's good. Yeah. One question: does Nikhil teach how to compute spectral spacifier in his class? Actually,
I think he will know, but I'm not sure.
he will do. Okay, good. Yeah. Let me just tell you one word then about how to compute this. Yeah. Because it becomes very like actually we saw one example, right? When you have a graph which is cut equivalent, but it's just not spectral equivalent at all. So it seems like computing spectral spacifier should be kind of harder than computing cut spacifier, because it's just a stronger notion. Okay. Now, it turns out that the same algorithm that we saw just work. Where did I? Yeah. Just, it turns out that if your graph is an expander again, then if you just take each of the edge and sample it with probability proportion to this, then you get spectral spacifier. Reason behind this, there is some reason behind it, but for now, we wouldn't have time to talk about it. But just want to mention that this algorithm is strong enough to even compute something stronger like spectral spacifier.
So is it the same algorithm, or are we doing any more changes?
So the change actually is almost like there is just some small change. That is, if you look at exact algorithm for cut spacifier on expander, the PE here that we set, the PE here that we set is this thing, right? Like we have 1 phi here. In spectral spacifier, you will just put it phi square. That's it. Yeah. So you might need to pay a bit more of a phi factor, but phi factor is like log, polylog, so doesn't matter that much, right? And really, based on this, because both spectral spacifier and cut spacifier, you can compute it using this super local information on both edge. That's why like the current dynamic algorithm to compute this guy just can be based on this algorithm. Yeah.
So this is what is used in dynamic graphs when
Yes.
variations also happen.
Yes, yeah. Because imagine like when you have a graph and if you need to say that this edge should be sampled with probability something like 1/λ. If this is arbitrary graph, when let's say you delete one edge here, this lambda might change, right? Like when you update an edge in somewhere far away, the lambda might change, and that's like not good for dynamic algorithm or local algorithm. But if you say down, okay, the probability to sample this is just like degree v, degree u, mean here. Then like when you do any update here, you add edge, you delete thing here, doesn't matter. You just wait until this guy, like the degree of u change quite a lot. Then you need to like change this thing. Yeah. Yeah. Okay. All right. Is there any question? Oh. Okay. All right. So if there's no question, I will just finish for today. How is the homework? Is it like I feel that this is actually a bit like harder than the last time, so might need to spend quite a bit of time on it. Yeah. Is that some part that you got stuck very hard, or you? Yeah. Yeah. So if there is some question that you feel you want a hint, we can just talk about it now too.